So let's talk about mathematical modeling with differential equations. Right now, we are not solving anything. We're not ready to solve these word problems, but we will in a future section. So this section is really important so that when we get to the section where we revisit the same word problems, but we're asked to solve, we're taking it step by step. So this section is focused on setting them up. And then in the future, hopefully setting them up will not be as hard of a battle because we would have had some practice with it. And we're more focused on the new stuff, which would be to actually solve the equations we come up with. So let's get started. Definition of a mathematical model is a mathematical description of a real world problem. We've worked with mathematical models throughout all of our math classes, really. We can use mathematical models in forms of diagrams in algebra class, calculus class. In order to understand a word problem, we drew a picture. We can use graphs. We can use Venn diagrams, many different ways that we can represent math and other ways than formulas. So it can be almost anything, really. So here, what we're using is a formula in order to represent what's happening in a real world situation. So the difference between direct and inverse proportionality, you may have learned this back in algebra, whether it was intermediate algebra, college algebra, or pre-calc. But if not, that's okay. So there's a relationship between the independent and the dependent variables. Sometimes they're directly proportional, and other times they are inversely or indirectly proportional. So a direct proportion is when y equals x, where c is some constant that can't be zero. And when we're indirectly or inversely proportional, then you see that y is equal to some constant, which could be 1 over x. So here are the different relationships between the proportionality relationships of x and y. Now, one type of word problem we're going to entertain is Newton's law of cooling and warming, and you may have already used this in your science classes, but we're going to take a look at the actual breakdown of the formula itself. So T of t, capital T of little t, represents the temperature at the time t. So essentially, we pick a time 3 minutes in, and it is a snapshot of what is the temperature at that moment. Let T sub m represent the temperature of the surrounding medium, which we will assume to be constant. So let's, for example, we use Newton's law of cooling and warming when we are trying to decide how long a body has been dead. So the body is really warm, 98.6 degrees. If we were in a perfect world, some people's body temperatures are not exactly 98.6, but that's the general temperature of a body. So knowing that a body starts at 98.6 degrees and dies in a room that has practically constant at 60, then we can test the temperature of a body to find out how long it's been dead by using this formula, which is kind of interesting. And that's actually what they do when they are out in the real world. So we are going to assume that the room that we are talking about, whether it's a dead body or a cup of coffee, is constant temperature, denoted T sub m. Let dt over dt, d big T over d little t, represent the rate at which the temperature of the body changes. Body could be a body medium, like a cup of coffee, or an actual human body, whatever we're talking about. So the change in temperature over time. Newton's law of cooling warming says that the change in temperature over time is directly proportional to the temperature in the surrounding room, subtract the temperature of the current status of the body. Thus, we have a direct proportion equation that says that you will find the change in temperature over time by the subtraction of these two, which I have, these are not the same in the PowerPoint, so one of these is wrong. Pause. It's supposed to be T minus Tm. So this is wrong. We got to switch these. This M should actually be here. I'm just going to put it there for now because I don't feel like going through the subscripts. So sorry, temperature of the body minus the room temperature times some constant, where the constant is the proportionality constant, which the only way to find that is to have a point that you know, a point in time where you knew the temperature of the surrounding room and the temperature of the body in question. Let's take a look at an example. Let's say that a cup of coffee cools according to Newton's law of cooling. Using the data from the graph of the temperature to estimate the constants, the surrounding temperature in the room, the initial temperature of the coffee, and the proportionality constant, which we'll have to use the equation to solve for. Let's walk through this step by step. Let me make myself some more room to do this problem for us. Now you're going to see in this particular problem that we're going to do a lot of estimating, and that would be because we only have a graph to work with. So when we only have a graph to work with, we kind of have to guesstimate, especially when it's not on graph paper, so it's not as easy to read. So if you're like, how is she getting these numbers? Just know that I'm guesstimating based on the window I'm looking in. So if I'm looking between 50 and 100, I'm picking a number based on what I think the line is hitting. Which means that I'm only looking for you guys to pull numbers in the correct window. So if we're looking for specifically this point and you tell me it's 120 on the y-axis, I'll know you're not looking in the right area because it's clearly between 50 and 100. So any number between 50 and 100 would make me happy. All right, so let's start off by taking the initial value. So we know that we're saying the initial value starts at 0 on the x-axis. So we look for where the graph is touching the y-axis, and we see it's about here. And again, it's a guesstimation. I'm going to estimate that this initial value is approximately at 170 degrees. So I'm going to say my initial temperature of the coffee is 170. Again, it could be any number between 150 and 200 that you are reading this estimation off of. That is just my estimation. Looks approximately 170. Next, I want to estimate the room temperature. So I'm going to move on to the room temperature. So if we think about it, the coffee starts up here at 170 degrees. And what does coffee do when it sits in a room? It cools down, and it will only cool down as low as the room temperature. Okay, you don't have a cup of coffee and you're sitting in a 70-degree room that goes below 70 degrees. That wouldn't make any sense. It would match the air around it. So knowing that, taking a look at this graph, we see that it is declining in temperature over time and then it bottoms out. Well, where it bottoms out makes sense that that must be the room temperature. So if I take a look at this line here as my bottoming out zone, then I can estimate that the room temperature is somewhere between 50 and 100. And I'm going to estimate, I went a little, let's see, I'm going to say it's about 60. Again, if you estimated anything between 50 and 100, I would be perfectly happy with that. So we're going to say that the temperature of the room is 60 degrees. Now I need to find the proportionality constant. In order to do that, I need a slope of a tangent line. I need dt dt, big dt over little dt. And I need a y value, t. So I need a t and I need a derivative. So I need to pick a point where I can fairly estimate what the slope of that line is. So I am going to pick this point here at the crest, because that point there looks like a slope of -1. If I look at this line here, I'm going to estimate the slope of this is -1. And I'm going to say, okay, this point looks like it maybe touches upon 15. And the y value, I'm going to estimate at 85. Again, I'm just estimating these numbers. You are going to be estimating as well. You're not all going to have the same numbers in there when you're taking the information from a very vague graph. But now that I can see that at time t equals 15 minutes, so 15 minutes after the coffee has been left alone on the desk, we are saying that the temperature of the coffee is approximately 85 degrees. We can now put this information together in order to find our constant, approximately. So using the formula, change in temperature over the change in time is equal to some constant temperature of the coffee at that time minus the surrounding room's temperature. We have -1 is equal to K times 85 minus 60. So we get -1 is equal to K times 25. So K is coming out to be -1 over 25 is the proportionality constant at a very, very rough estimate, considering all these numbers came from a vague graph. So the last step is just to put them into the formula so that we have a formula so that in the next couple sections when we start revisiting these word problems and they actually give us something to solve for, we know how to get the original formula. So substituting this all back in, I would say that, okay, the change in temperature over the change in time can be found by multiplying the proportionality constant -1 over 25 times the temperature of the coffee at a specific moment minus 60 degrees, which is assumed to be a constant room temperature. Also, the information that we should put in our solution is that T naught equals 170, or we can write it as T of 0 is 170. So before we start counting the cooling time, our coffee was at 170 degrees. Okay, so that's all we're looking for to do in this particular problem, is to pull in the information, and we need the constant and the room temperature to have some place to start with an initial point. Let's talk about population dynamics. So P of T represents a total population at a specific time. Assuming the rate of the population growth is proportional to the size of the proportion, giving us the differential equation dP dt is equal to K times P, where K is your proportionality constant. Then if we take a look at a particular population dynamic problem, determine the differential equation for the population of a country when individuals are allowed to immigrate into the country. So immigration means that people are coming into your country at a constant rate of R. What is the differential equation for a population of a country when the individuals are allowed to emigrate, which means leave the country at a constant rate of R? So this one is actually more straightforward than you would think. We have the basic equation from the last slide, which said that the change in population over the change in time is directly proportional to a proportionality constant times the proportion. Okay, well, we're not given any specific information here, so there's no way that we can find the proportionality constant. We have no points or graphs to work with, nor do we have an initial population to find either. So really, we're just looking at the difference between immigration and emigration. And since immigration adds to the country's population total because people are coming into the country, and emigration is people leaving the country, then it is as simple as your immigration formula is going to be the change in population over the change in time is equal to the basic population proportionality plus the rate at which people are coming into the country. And your immigrate formula, oops, it's only one M. That is a G. Is going to be the change in population over the change in time is equal to K times P, but minus the constant rate at which people are leaving the country. Okay, so sometimes these problems are more straightforward than you would expect, which is why I wanted to include this example. Last example we're going to talk about today is the mixtures, which are a bit more complicated, but again, we're just setting up at this time. So A of T is going to represent the amount of material in a solution, whether it be salt or peroxide or whatever we're adding to a particular solution, whatever mixture we're making, hydrochloric acid, at some specific time T. dA dt represents the rate of accumulation, so the amount of the material over a specific time that we have inflow and outflow. So the change in amount over the change in time is equivalent to the rate that we have stuff coming in minus the rate that we have stuff flowing out. And the rate in is going to be found by taking the concentration of the material that is being flowed into the basin or the whatever we are using as to hold the material in general, times the rate at which it's flowing in. And similarly, rate out would be the concentration of the material that's in the basin that's holding all of the solution and the rate that it's coming out of that particular holder. So let's take a look at this example. So we have that, let me make some room. Suppose that we have a large mixing tank, initially holds 300 gallons of water in which 50 pounds of salt have been dissolved. Pure water is pumped into the tank at a rate of 3 gallons per minute, and the solution is well stirred. It is then pumped out at the same rate. Determine a differential equation for the amount of salt in the tank at any given positive time. Okay, so let's take a look at this one. Again, our differential equation, or basic differential equation, the amount in the tank over the amount of time is equal to the input rate, specifically the input rate of salt, minus the output rate. So we need to calculate the input and the output. So for input, it is the concentration of salt times the rate at which it's coming in. If we look back at the problem, we are talking about pure water, which means that there is 0% salt. And we're multiplying that by 3 gallons per minute, as that is how fast the water is being pumped into the tank, which gives us how fast is salt being pumped in? 0 gallons per minute. Rate out. Well, when we are out, the initial value is 50 pounds in 3 gallons of water, so it'd be 50 over 300. But remember, there's water being poured in at the same time that we are taking this solution out of the tank, which means that it's not going to be constant at 50 pounds of salt per 300 gallons. It's going to dilute as the pure water is being poured into the tank. So we will denote the rate that it's going out is the amount of salt at a specific time over the 300 gallons, because it's a 300-gallon tank. So it's just replacing water in there. It's not like you're filling it up more. Okay, and that is going to be amount of pounds of salt per minute, the rate at which it's going out. And we know that it's going out 3 gallons per minute because it was stated in the problem that the output rate is the same as the input. So if we do our math, this gives us an output rate of salt at the amount of salt in the tank at any given time over 100 pounds per minute. Okay, because we, oops, this is not per minute, this is pounds per gallon. I'm going to say, if we look at our dimensional analysis, we should be able to cross cancel labels and know what we're left with, which is how I get pounds per minute. So I just labeled that one wrong by accident. So our final result, our change in amount of salt over the change in time, is going to be the input rate minus the output rate, where our initial value is 50. And that's it. That's all we are putting together. Reading the problem, understanding how to put things in the correct places, and setting it up. And then there would be additional information if we were asked to solve this. Right now we have nothing to solve. All right, so that concludes setting up mathematical models for differential equations.